In this video, I'm going over our application problems with our exponential and log functions. So in the first example, the city's population was initially 22,300, and it's been dropping. So we have decay here. So we're subtracting 2.5%. So I know here 2.5%, which is also 0.025. How long will it take for the population? So how long, so we're looking for time, will it take for the population to drop below 10,000? So this is the final amount, which is what our equation was always equal to, which makes sense because we're dropping. So we need to set up our formula as 10,000 is equal to the original, which is 22,300, then times 1 minus our rate, so 0.025, but now raising that to the t power. Now notice a little different, but what I'm going to go ahead and do is notice how we are solving for our exponential here. But before I do that, I'll go ahead and solve what's inside the parentheses. So I've got 10,000 is equal to 22,300, now times 0.975, so subtracting my rate, now raised to the t power. Now notice we're solving for the exponent, but right now it's not by itself, it's being multiplied by 22,000. So first we're going to divide both sides by 22,300. So now here when dividing, you should get 0.448, which is equal to our base 0.975, now raised to the t power. Now here we are solving for an exponent. So that means now to get the inverse, right? Because think about inverse operations, we're going to write this as a log. So this is now the log base. Well, the base is 0.975 of 0.448, which is now equal to t. So now notice to solve for time, we have this log value here, which, if you recall, is our change of base, where we have the log of 0.448, divide that by log of 0.975. Then here you will get the approximate year, which makes t approximately 32 years. So go ahead and pause the video now and try this try on your own. And here we go. You should have noticed in this problem that you are increasing by this rate. So we have 1 plus our rate, which is 0.033. Then we started at 147,000. Our final amount is 200,000 people. When will the population? So again, you're looking for time in years. So here you should have set this up as, so our final, which is 200,000, because that's what we're increasing to, is equal to 147,000 times 1 plus 0.033, but now raised to the t power, because that's what you're solving for. Now here I can go ahead and simplify what's inside. So this is 200,000 equal to, but now just at least inside the parentheses, now we have 1.033 raised to the t power as your base. Now as we go through and solve, if you're multiplying, then you need to divide by 147,000. And so here now, when canceling out, you end up getting approximately 1.361, which is equal to now our base 1.033 being raised to the t power. So now because you're solving for the exponent, you should have written this as a log, the inverse. So this is the same as log base 1.033 of 1.361, which is equal to t, your exponent. And here you should have noticed that this is the change of base formula here in order to simplify. So you have the log of 1.36 divided by log of 1.033. which is approximately 9 years. So when will the population, so if we're in 2023, in approximately 2032. So the population of kangaroos now in our example is decreasing. So again, we are subtracting by our rate 6.3% or 0.063. This year, so this is our current 35,000 kangaroos were located. At the current rate, how many kangaroos would there have been in 2019? So we are looking for how many were initially. So this 35,000 this year is the final amount. We are looking for the initial that back in 2019, which was 4 years ago. So as we set this one up, we're given the final, which is 35,000. Now that's equal to, we don't know what the initial is, so I'll put P or principal for our initial. Then times 1 minus, because we're decreasing, by our rate of 0.063 raised to the 4th power because we're going back 4 years ago in 2019. So now here simplifying, I've got 35,000 is equal to P times. So subtracting from 1, we have 0.937 raised to the 4th power. Now, technically, we have a value here being raised to an exponent. So this can just be put in the calculator. So now I've got 35,000 is equal to P times, putting this value to the 4th power, you should get 0.771. So now we can solve for P, but if it's being multiplied by our decimal value here, then we're going to do the opposite, which is divide by that decimal value here. And so now I've got that P, the initial, back in 2019 was approximately 45,405 kangaroos. Go ahead now and pause the video and try the U-try on your own. And here we go. So again, some keywords that you should have noticed are, again, we're decreasing. So we're subtracting, we have decay, 4.5%. So 0.045 is our rate since 2019. So again, 4 years ago. At the end of 2022, sorry about that. So that probably is, we'll make it 2023 since we're now in 2023. So 4 years ago, 85,000 Christmas trees were planted. How many Christmas trees were planted? So here we have the final amount. We're looking for where we started. So again, the final amount in this year is 85,000 Christmas trees is equal to our principal where we're starting, which is 1 minus our rate, 0.045, raised to the t, which is 4 years. And so now we're going to go through and solve. So here I've got 85,000, which is equal to P times, so that's 0.955 being raised to the 4th power. So here, after, you could raise this and put this in the calculator. I'm going to go ahead though and show that whatever we end up with here, we're going to divide by 0.955, which is being raised to the 4th power. So since this is being multiplied by P, we're now going to divide by that value. And so here, the initial amount of Christmas trees that you should have gotten is approximately 102,189 Christmas trees. And so now in example 3, as we're reading through this, how Tony invested money in a savings account, it grew at a rate of 6% or 0.06 compounded. So now we're dealing with a compounding formula. Compounded how often? Weekly, which means we have n, which is equal to 52. So we're going to use our formula where we are compounding with that value of n. And after 5 years, so here's our T, his initial investment was worth. So this is the final amount. What was his initial? So again, we're looking for P, the initial investment. So again, setting this up, $20,024 or $2,024.44 is equal to our initial, which is P, times 1 plus. Now keep in mind, this is a compounding. So we have our rate 0.06 divided by 52, still raised to the 5 years power, but then don't forget to also multiply by that value of n, which is 52. So now notice here, we can just put that value in the calculator. $2,024.44 is equal to 1.35 P approximately. Now, if we're multiplying P by 1.35, then we need to now divide by 1.35. And so now P is approximately $1,500. That was the initial investment. Go ahead and pause the video and try this. You try on your own. And here we go. So Katie invested some of her money into an account that grew at that rate of 8%, 0.08. Compounded, so compounded quarterly, where N represents 4. After 9 years, so here's our T, she accumulated, so this is the final amount of $1,632. How much money did she originally put? So again, you're looking for P. So setting this up, $1,632 is equal to, sorry about that. We have that initial, so P times compounding 1 plus, again, our rate 0.08, but now divided by 4. Raised to the 9 years, but again, don't forget to multiply by that N value, which was 4 for quarterly. So now here, notice, again, you can just put this in your calculator. You've got 1,632 is equal to P times 2.04. So now here, if you're multiplying by P, now you need to divide that value. So here, P, the original amount, was approximately $800.04. And so now in example 4, we are talking about population, but using a different formula. So P of T for population is equal to representing our function here, starting back in 1980. So what would the population have been in 2000 if the growth continued at the same rate? So that means if we want to know what is the final population, we're looking for P. And what would have been in 2000, which means if we're starting in 1980, we have now had 20 years pass. So we are using this formula here to identify what is the value of P. So P is equal to 720,500 times 1.022 raised to the what power? Well, what is T? 20 years. So now this is just straightforward, putting this in the calculator, and you get that the population is approximately 1,113,401 people. So now in part B, in what year would the population of Arendelle reach 1 million people? So now the 1 million represents the population, that final amount. We want to know how long it takes. So now P, which is 1 million, that is equal to 720,500 times 1.022 to the T power, because that is what we are looking for. Then again, notice how we have our base raised to the exponent that's being multiplied. So we're going to first divide, opposite operation, do the inverse. So 720,500. So now here, when you divide, you get approximately 1.39, which is equal to 1.022 raised to the T power. So now I can continue with the inverse, but to bring this exponent down, we write the inverse, which is the log. So this is now log with a base of 1.022 of 1.39, which is equal to t. So now notice what can we use here to calculate t? Change of base. So now I've got the log of 1.39 divided by log of 1.022, which is approximately 15 years. So if we started in 1980, then in what year? Approximately 1995. So go ahead now, pause the video. And so in this you try, here, if you were to read through this, you would see that we have in Alex investing money into a hedge fund that has a rate of 12.3% or 0.123 compounded continuously, which means we're going to use our PERT formula because we're compounding continuously. And Alex decided to withdraw money, but 6 years later. So there's your time. If he withdrew, how much money did he invest initially? So this was the final amount that he had. We're looking for how much did he invest initially, which is P. So you should have set this up, $27,604 is equal to P times E, our function, but raised to the rate times time power, which is 0.123 times 6 because of our years. So now here, if you notice, we can put our E function in the calculator. So I've got 27,604, which is equal to approximately P times 2.09. So now to solve for P, if it's being multiplied, then divide by 2.09. And here you end up with P is approximately $13,196.62.